Okay, so we have learned how to solve exponential equations. Now it's time to start solving logarithmic equations. And our general strategy, at least the strategy we're going to use for this first couple, there's like two different strategies. Since I have one natural log of x and I have numbers, what I want to do is I want to isolate my natural log of x. So just like absolute value when we solved for it, we are going to solve for the natural log of x first. So we are going to subtract 4 from both sides. We'll get 3 ln x equals 12. I am going to then divide by 3, giving me the natural log of x is equal to 4. And then I'm going to flip this back into exponential form. So I have an implied base e here. So this is really e to the 4th equals x. And that's my number. I can decimal approximate e to the 4th, but I'm just going to leave it because that's the most exact answer I can come up with. Alright, so in that case, I just had the one natural log and I isolated it. So this time, my strategy, I have two natural logs and a number on the other side. So what I want to do is combine my two logs into a single log. So in the first one I only had one log, so I didn't have to do that. But I do want to combine my two different logs into a single log. They're both log base 2. So the way that I do that is I notice that these have a plus between them, so that means that I can combine them as multiplication. So it's log base 2 of 5 times 2x minus 3 is equal to 3. So I can do one more simplification step. I can multiply this through here. So this is log base 2 of 10x minus 15 equals 3. And now just like I did up here, right, I put it back in exponential form, I'm going to put this back in exponential form. So I have 2 cubed equals this. So 2 cubed equals 10x minus 15. Right, 2 cubed is 8, so we'll replace the 2 cubed. And then we will just solve for x. I will add 15 to both sides here. And I will get, what, 23 equals 10x. I divide both sides by 10, and I get x equals 23 over 10. And there's my answer. Now, something that I haven't talked about yet, because we haven't really run into it yet, but log equations, I do need to be very careful with them because we've talked about the fact that the domain of this log is basically wherever 2x minus 3 is greater than 0. So I cannot take the log of 0, I cannot take the log of a negative number, and so we should just double check that neither one of these is going to give me a negative answer. Now e to the 4th is totally positive, so that's not an issue. I can put that into my natural log of x. And so I have 23 over 10. I don't have, this is just a number, so if I put in this, I would get 43 over 10, which is bigger than 4, so minus 3, so it'd be greater than 0. So we're fine there. So this is a solution. But we do have to just double check those because we're not allowed to take the log of a negative number, and that is because, right, if I put something back in exponential form, right, if I have log base 2 of something here equals negative 2, actually that's not true, I want to put a negative 2 here, equals something, then I have 2 to the x equals negative 2. And that, I can't make that do that, right? I'm raising a positive base to a power, which is always going to give me a positive number, because even negative powers give me just small numbers, not negative, for I think the third time that at least I've said that. Okay, so let's do another one, kind of like that. So very similar to the previous one. So all we need to do this time is solve for the natural log. I only have one of them, so I'm just going to divide both sides by 2 and get the natural log of x plus 1 equals 5, and then I'm going to exponentiate is what we call it, sort of flip it back into exponential form. So this would be e to the 5th equals x plus 1. So x is e to the 5th minus 1. And e to the 5th is quite a large number, so it's going to be greater. It's not going to affect this. If I put it in here, it will be positive. Alright, so now we have kind of logs all over the place here. Now in this particular case, since I have logs on both sides, and that's all I have, I mean this primarily works with that, is I'm going to use, remember when we were doing like exponential functions with the same base, so if I had 2 to the x equals 2 cubed, then if I have the same base, then the powers must be equal. So this would be x equals 3. I mean, that's a really basic idea. If I have log base something equals a log the same base of something else, then the two things have to be equal. So my goal here is actually to get just log equals log on this side. So I can combine these two because I have a plus between them. So this would be the log of 2 times 4x plus 2. Combining these two into a single log equals the log of x minus 3. And now I can kind of employ this strategy. I have the log of something equals the log with the same base. This is implied, it's a 10. So that means basically I can just think, okay, well if these two things must be equal, then so must these two things be equal. So that means that 2 times 4x plus 2 equals x minus 3. So I'm just going to open my parentheses here. I get 8x plus 4 equals x minus 3. If I move this x over here, I get 7x equals, and I'm going to subtract 4 over here, so I get negative 7, right? I just did two steps in one. I subtracted x, and then I subtracted 4. So now I get 7x equals negative 7, and I get x equals negative 1. Okay, I'm always very suspicious when I get a negative number because I know I'm going to plug it in here. And I notice as soon as and even if, so now negative 1 doesn't work in either one, because if I plug in negative 1 here, I get negative 4 plus 2, which is negative 2. If I plug it in here, it ends up being negative 4. So it doesn't work in either one. Had this one been x plus 3 instead, and it worked in this one, but not in this one, it's still not a solution because it has to work in all. So this one ends up being a no solution case. Okay? So basically, that did not work. Alright. Alright, so sometimes we also run into things like, so this is sort of that one-to-one idea again. I have the natural log of something equals the natural log of something else. And so that means that since I have natural logs on both sides, they both have base e, and that's all I have, that means that these things must be equal as well. So that means x squared equals 2x plus 3. So that means I suddenly have a quadratic, right? And so I'm going to move everything to this side because I'm going to try to factor it, and I always like my x squareds to be positive. So I have x minus 3 times x plus 1 equals 0. Alright, so I get x equals 3 from that one, and x equals negative 1. So just, I know for sure the 3 is going to work because I'll get 9 here, and then this will be also positive, so this works. How about negative 1? Let's see, if I put negative 1 in here and square it, I get positive 1, so that's fine. If I plug in negative 1 here, I get negative 2 plus 3, which is also positive and not 0, so they both work in this case. So it's not that my answer can't be negative, just I'm usually extra suspicious when it is negative because I know that I can't take the log of a negative number. Alright, so now let's go to a more realistic, not just equation solving. So let's think about this. So now, before we couldn't really solve for t because we didn't have a way to bring it down and solve for it, but now we actually do. So let's say that a population of a small town is modeled by p of t, which is 1100 e to the 0.5 t, or the half t, where t is measured in years. And approximately how many years, so we're going to solve for t, will it take for the population to reach 5,000? So this is a future population, so that means I'm going to set this equal to 5,000, and then I have this original equation, 0.5t. All right, so the way that I solve these is I solve for the e, right? So this is really kind of going back to an exponential function a little bit, but I wanted to do a realistic kind of example of mixing them together. I'm going to divide both sides by 1100. All right, when I do that, I get, let's see, I have 5,000 divided by 1100, which is, let's say, 4.55. And this is equal to e to the 0.5t. And now I use my natural log of both sides. I have the natural log of 4.55 equals the natural log of e to the 0.5t. And then hopefully I remember that the natural log of e to a power is just the power. So this is 0.5t equals the natural log of 4.55. I solve for t by dividing both sides by 0.5, and I end up with t is approximately, actually I did that in the step before. You can kind of see I had already worked this out just to make sure it worked. The natural log of 4.55 divided by 0.5, which is 3.03, so approximately 3 years, we'll say. Okay, and so now we know how to solve both logarithmic and exponential equations.